Welcome back to this Forge College Explainer. So we're jumping right from our last lesson, applying scalability solutions, straight into the Mastering Program Architecture on Solana module. Our focus today, resource optimization patterns for programs. Now, you've already tackled sharding accounts and batching instructions to pump up your transaction throughput, right? But honestly, throughput is only half the battle. Now we need to optimize the actual workload so your programs don't just burn through precious compute and storage resources for no reason. Let's quickly scan the agenda. We're hitting the repeated compute problem, the PDA cache pattern, guards and account packing, measuring the savings, and finally wrapping up with some core mantras. All right, section 1, the repeated compute problem, or as I like to call it, why doing the exact same work twice is a really bad idea. To hit peak performance, you kind of have to channel your inner lazy but brilliant engineer. Seriously, why pay for the same math twice? Just imagine you've got a smart contract, and it needs to run this massive 1,000 iteration hashing loop just to generate a specific state derivation. If multiple users, or even the same user, keep requesting that exact same result within a tiny time frame, are you really going to force your program to grind through all 1,000 iterations and eat that compute cost every single time? No way. It basically comes down to this. It's like building a clock from scratch every single time someone asks you for the time, versus just glancing at a clock on the wall. We want to be the person just glancing at the clock. Instead of rerunning heavy computations, we just want to read the answer we've already figured out and written down. Which brings us right to section 2, the PDA cache pattern. Consider this our sticky note solution. It's the absolute hero of this entire blueprint. So what is it? A PDA, or program-derived address. Cache is all about storing a computed result, along with a timestamp, at a predictable, deterministically seeded address. Because we derive this address from a known seed, like a user's pub key and a simple string like cache, our program knows exactly where this metaphorical sticky note is. We can grab our stored answer instantly, without wasting compute on expensive, complicated lookups. Moving to section 3, guards and account packing. Because having a cache is great, but protecting that compute is crucial. We need a padlock. We need what's called an early exit guard. This is just a super cheap, deterministic check. Basically, you check the timestamp on your cache against a defined time to live, or TTL. If the network time says the data is still fresh, boom, you bail out immediately. You skip the expensive computation path entirely and just return the saved value. It saves massive amounts of compute. The logic flow is actually pretty beautiful. Step 1, check the clock. Step 2, ask, is the data fresh? Step 3, if yes, you hit that early exit and happily return the cached value. But step 4, if it's stale, or if it's the very first time and the cache doesn't exist yet, well, then you have to exhaustingly grind through the heavy compute, find the answer, and save it for next time. Now, when you do save that state, you have to keep it insanely small. We're talking 32 bytes for the value itself, plus a little extra for the timestamp and TTL. Why so small? Because on the blockchain, storing data costs rent, and reading data costs compute. By keeping the state tiny, you minimize rent and dramatically slash your serialization overhead. Think about it like packing for a trip. You wouldn't unpack a giant, messy suitcase just to find your toothbrush, right? The same logic applies here. If you deserialize a massive collection of unrelated accounts just to read one tiny 32-byte cache value, you're just throwing compute away. You have to restrict your deserialization to only the cached account. All right, section 4, measuring the savings. Time to actually prove this pattern works. We need hard data from our local validator tests. On the very first invocation, the cache miss, you absolutely expect a high compute hit because you're running that heavy loop and writing to the account. But on any subsequent call within the TTL, those are your cache hits. You're just doing a cheap time check, 0 account writes, and walking away with a beautifully low compute cost. And of course, once the TTL expires, you're right back to a high compute cost to recompute and write again. And to make sure you aren't just writing bad code that accidentally masks your optimizations, your tests have to hit some strict validation checkpoints. First, you need a measurable compute reduction on a cache hit. Second, single write behavior, meaning you only write on a miss. And third, functional correctness. Those cheap cache hits absolutely cannot modify your timestamp or your cached value. Finally, section 5, core mantras, the absolute rules of optimization for any master architect. Mantra number 1, early exit first, compute only when needed. You must always guard your most expensive execution paths with the absolute cheapest deterministic checks you can find. Keep the heavy machinery turned off whenever possible. Mantra number 2, store compactly, write rarely.
Keep those account footprints tiny to save on rent and only write to them when it's absolutely necessary. Bloated serialization is the enemy here.
So once you've nailed this PDA cache pattern, you'll be perfectly prepped for our next lesson, designing for high-frequency transactions. We'll be taking these exact patterns and seeing how they hold up under the intense stress of sustained concurrent load. So how much compute is your next program going to save? I really hope this Forge College Explainer helps you engineer some brilliant, incredibly lazy, and highly efficient solutions. Make sure you head over to forge.college to dive deeper into this subject and master even more Web3 architectures. Catch you in the next one.